Great to be here.
Well, good afternoon, everybody. Good afternoon, and why don't we go ahead and get started. Welcome. Thanks very much for being here. For those of you that I haven't met, I'm Rod Nearon. I'm Acting Chancellor and Provost and Executive Vice Chancellor for Academic Affairs. My staff are having a lot of fun with that. They're not sure whether they should call me the Chovost or the Chancellor, but we may take a poll on that and see which one you like the best. But welcome. It's really a great pleasure to have everybody here for this, which is the second annual Chancellor's Distinguished Lecture, made possible by the Damrau Endowed Lectureship Fund. The fund was created by Drs. Lenny and Bob Damrau, and they did this in 2014 in honor of their parents who did not have the opportunity themselves to attend college but greatly valued education. And of course, this is an enormously generous contribution on their behalf. Really appreciate it. It'll make a huge difference to the campus. And of course, it's a reflection of their personal passion for science and the desire to share the excellence and great ideas that there are with the community very broadly. So it's an annual free lecture series that focuses on subjects of broad general interest and appeal in the STEM area, so science, technology, engineering, and math. And for those of you who don't know, Lenny Damrau was a longtime professor in chemistry before taking up a career in computer science. She worked in information systems at Children's Hospital for more than 20 years. And after retiring from there, she came to the CU Denver campus to work in the registrar's office. Bob was one of the original faculty members on this campus, been here since 1968, highly regarded as a chemistry faculty member and as a mentor to many young pre-tenure faculty, a guiding light on the campus and in particular in the chemistry department. Today he wears multiple hats. I'm not sure, maybe he has more than anybody else. Professor of Chemistry, Associate Vice Chancellor for Research, and Special Assistant to the Provost. And the acting chancellor tells me that the provost needs a lot of special assistance. I'm glad to have Bob help. So we're extraordinarily grateful to the Damraus for endowing this lectureship. Really excited for this, the second in what we anticipate will be a long series of interesting and stimulating lectures. Please join me in thanking the Damraus once again for their This evening's speaker, Dr. Ed Lazowska, is one of the world's foremost scholars in the area of high-performance computing and communication systems. And let me give you a very brief outline of his many accomplishments. He holds the Bill and Melinda Gates Chair of Computer Science and Engineering at the University of Washington, where he's also the founding director of the eScience Institute. He's a member of the National Academy of Engineering, a fellow of the American Academy of Arts and Sciences. He's also a long-time advocate for increasing participation of women in the sciences, serves on the Executive Advisory Council of the National Center for Women and Information Technology, and on the National Research Council's Committee on Women in Science, Engineering, and Medicine. He's been a member of the Technical Advisory Board for Microsoft since its inception, serves as a board member on numerous high-tech companies, venture firms, technology-oriented civic organizations. Dr. Lazowska received his bachelor's degree from Brown University and his PhD from the University of Toronto. Among the many PhD students he's advised at the University of Washington is our own John Bennett, professor of computer science, leader of the InWorks initiative, and Associate Vice Chancellor for Innovation Initiatives. Please join me in welcoming our speaker tonight, Dr. Lazowska, our second ever CU Denver Chancellor's Distinguished Lecturer.
okay? Mutes all microphones, not just this microphone. Okay. So there were 4 amazing things that happened in 1969. Can you remember a few of them? What happened in 69? The moon, great. Person landed on the moon, just an astonishing engineering accomplishment and something that really raised our aspirations for what we could do. What else? Well, I'm going to give you partial credit. Woodstock. Nobody remembers Woodstock. They were all stoned and rolling in the mud, but it happened. What else? The Mets won the World Series. It's happened once since then, okay? And here's the 4th. The first packet of data flowed over ARPANET, the precursor to today's internet, okay? And back then, this is the literal napkin diagram of ARPANET at the time. There were 4 sites on the West Coast. On the right there is the log that Charlie Klein, a programmer of Len Kleinrock's at UCLA, used to log the packet transmission to SRI. At this point, the internet, the ARPANET, was not used for shopping or pornography or reading the newspaper or anything like that. It was for sharing large, expensive time-sharing computers, okay? So what Charlie was trying to do was log into a PDP-10 remote system at SRI, and the first packet that flowed over the network contained the characters L and O, the first 2 characters of the word login, and then the network crashed, right? So some things have never changed. Now the question is, with 45 years of hindsight, which of those was more important? And I claim that unless you're really big into Tang and Velcro, the alleged but false byproducts of the space program, it's really the internet. Billions of people use it today, right? And the reason is we've been hooked to these exponentials. And I'm going to spend a minute belaboring this exponential thing. There's this old story about the pharaoh, whoever it was, that commissioned the invention of the game of chess, all right? And he said to the inventor of the game for him, "This is so fantastic that I'll give you anything you want." And what the inventor asked for was 1 grain of rice for the first square of the chessboard, and 2 for the second, and 4 for the third, and 8 for the fourth. And the pharaoh said, "Sure, no problem." And indeed, it was no problem. And even at the end of the first row, it's only 128 grains of rice. And as you move up there, though, halfway up, you're in sort of the 4 million grains of rice. And, you know, by the time you get to the upper right, you're talking about a lot of rice, all right? So that's sort of the negative version of this. The positive version in computing is that everything has been making this exponential progress for decades. Processing capacity, storage capacity, network bandwidth, sensors. Astonishingly, algorithms, which Moore's law has nothing to do with, have in some cases made more progress even, all right, than the hardware. That's just sort of human intellect at work, okay? So there are 2 ways to utilize this. One is you get constant capability at exponentially decreasing cost. You can't really read this, but here's what it is. It's storage price per megabyte on a semi-log scale. So it's a straight line. And what that shows is that at fixed periods of time, right, you can get a megabyte for half the price that it used to cost, okay? The alternative is exponentially increasing capability at a constant cost. So this is Intel processor performance. And what you see again on semi-log is that it's a straight line. So every year and a half or so, the amount of processing you can buy for $50 doubles, right? And this is unlike almost anything we experience in our daily lives. So the result is that the processing capability of an early mainframe is now truly in an electronic greeting card, okay? And we talked about Apollo 11, the processing capability, the entire aggregate millions of instructions per second that got Apollo 11 to the moon is in a Furby, okay? So I got this from a DARPA program manager's slide, so it must be true. And, you know, this is not the best sort of social use of this technology, but it's still utterly astonishing. So one more thing, just to belabor this, let's think about automobiles over the past 45 years. There has been no change. Same size, same speed, same efficiency, same value, all right? You know, if automobiles had been on the same curve as microprocessors over that period of time, you know, a car would be about 1/5 of an inch long. It would go 6 million miles an hour, so coast to coast in less than 2 seconds. It would do that on a half cup of fuel, and it would cost $10, right? So it's cars that are what we're used to, or airplanes, which have maybe doubled in speed in the past 50 years, or tripled, or something like that, okay? So it's just utterly mind-blowing. Now, the question is, great, that's fine, that's a while ago, what have you done for me lately? And let me talk about what we're doing now. All of these exponential improvements in technology are bringing about this big data revolution. So there are sensors everywhere. If you just think about your iPhone or your Android phone, it's got a dozen sensors in it, okay? You know, it's got GPS, it's of course got a camera, it's got Wi-Fi, it's got Bluetooth. You know, it's just remarkable what you're carrying around in your pocket, and you've got a Fitbit and things like that. More generally, all information is created in a digital form, so you don't have to digitize it before you can use it. Storage is cheap, so you can store just about everything. Network bandwidth is increasing dramatically, so you can move the data to where you need to. Computation is dramatically more scalable than it used to be. And I'll say more about things like Amazon Web Services in a bit, but the astonishing thing now is that 1,000 processors for one day cost the same as one processor for 1,000 days. And that's new in the past 5 years, and it's utterly revolutionary, right? You can rent vast amounts of processing power for a day to accomplish something that previously would have cost enormous amounts of money. You can do a startup company with no capital investment at all, okay? So that's basically the story. What is big data? This is my favorite slide. Imagine being the person who had to give the talk that followed this guy. It says, big data is like teenage sex. Everyone talks about it. Nobody knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they're doing it. Here's the way I think about what's going on, all right? I have this 2010 thing here because back at the turn of the decade, I was asked by this national tech blog to talk about what interesting had happened in the past 10 years and what was going to happen in the next 10 years. And this is, I think, the only prediction I made that has turned out to be right. And what I said was we were going to spend this decade making everything smart. And it is data analytics that are enabling everything to become smart. So that's what computer science is doing this decade. And let me give you quickie examples of each of these. So smart homes, this is, for example, a colleague of mine at the University of Washington, Shwetak Patel, who has built a sensor that you plug in anywhere in your home, and it completely disaggregates your home energy usage, so you know how much power each device is using. And it does this by using the noise on your power line as the signal. Every electric motor puts a signal on the line. A compact fluorescent light puts a signal on the line. When you flip a switch, it puts a spike on the line. And what he does is learn these noise signals and use them to categorize your power consumption. I mentioned to someone earlier today that when he first began experimenting in his home, he discovered that the single device using the largest amount of power in his house was his stupid Comcast set-top box, okay, which was consuming 16% of his electric power because it's an outmoded, non-energy compliant personal computer that's sitting there in the basement heating the room, okay? I could say more, but let me move ahead. Smart cars, you're familiar with Google's robot cars and things like this. Whether or not you think this is a good idea, I think, personally, I live in a part of Seattle with completely clueless drivers, and I have dramatically greater confidence in autonomous vehicles than in the people I bicycle around every day. But the important thing is that much of this technology, even if you believe that robot cars are sort of the Jetsons' future, is in cars you buy today. Many of you have cars with adaptive cruise control. Many of you have cars with self-parking, whether or not you have the nerve to use them, all right? These are all byproducts of this technology, and it makes an amazing, amazing difference. And again, Google is in the autonomous vehicle business not because they want to be General Motors, it's because they want to be the data purveyors to the vehicle industry in the future. And the way to figure out what kind of data those vehicles need is to build them and deploy them on the roads, okay? Smart health. I've mentioned to a few people today that I was part of a study that Lee Hood, the biotech person in Seattle, did between 1 year and 2 years ago, in which we got complete genome sequencing, and then every quarter we got complete blood work, microbiome analysis, saliva analysis. They, snooped on our Fitbits and things like this, and it's quite remarkable. This is the future of medicine, in which you transition medicine from a sickness industry to a wellness industry, all right? And here's some things I discovered about myself. For example, the first set of blood work I got, my mercury was pinning the needle, all right? Not good. It explains a lot of things. And through a coaching interaction, they elicited from me that I was eating tuna sushi 3 days a week for lunch, and I did nothing but switch from tuna sushi to salmon sushi, and my blood mercury dropped in half, okay? Another example is I had a an anomaly visible in my blood work that was likely attributable to a vitamin B deficiency, and it turned out that I had a genetic inhibitor to the absorption of vitamin B. So they changed me to a more active form of vitamin B. I hadn't noticed any ill effects from either of these, but the point is, in general, this is really, I think, the future of many forms of medicine, and it's going to completely revolutionize, for example, the pharmaceutical industry, in which we move in the direction of producing large numbers of drugs in small quantities targeted to specific individuals, instead of vast amounts of a relatively small number of drugs that are misprescribed because you don't know what their impact will be on a single individual. Robots, for decades, have been robots in what we call structured environments. They're bolted to the floor in automotive assembly plants, right? And now, you know, Consumer Reports doesn't think iRobot is the smartest vacuum in the world, okay? But nonetheless, it's quite remarkable that this thing can cruise your house. Our eScience Institute at the University of Washington has one of these things, and it more or less cleans things up, and it doesn't matter whether the chairs today are in the same place they were yesterday. It just figures it out. The cat doesn't bother it, except for the fur balls, okay? My colleague Zoran Popovic at the University of Washington, along with David Baker, built a program called Foldit. Have any of you played Foldit? Great. So Foldit is this astonishing video game in which people do protein folding, right? And the person who first started this human computation business a number of years ago, a young guy named Luis von Ahn at Carnegie Mellon, began by getting data on the amount of time that is spent by people worldwide every day playing computer solitaire. Okay, and you know, before Alaska Airlines introduced digiplayers, you used to be able to walk from the back of the plane to the front of the plane, and you know, 2 out of 3 people would be playing solitaire. This was actually introduced by Microsoft as a mouse training game when they first introduced Windows. They just wanted people to practice pointing and clicking, so they created this solitaire game. And people are willing to waste vast amounts of time in return for points. Okay, so Luis calculated that 1.5 days of computer solitaire playing is the number of person-hours it took to build the Panama Canal, okay? So the question is, could you turn some tiny portion of that into productive work? And that's what Foldit does, okay? It's just utterly remarkable. Several thousand gamers 2 years ago solved an AIDS-related protein structure problem that had baffled the science community for 11 years, all right? So one of the cool things about this game is that it takes advantage of the different capabilities of different people on the team, all right? So having 1,000 people who have different approaches is more valuable than having 1,000 people who are clones of one another. And that's what you'd expect from a sort of social setting, a workshop setting, but you wouldn't necessarily expect a computer game to be able to bring that up. Zoran has since turned his attention to education. The Gates Foundation has funded him to roll out an incredible adaptive game for teaching algebra to elementary school kids. And the results from this are astonishing. That's a slide from the Norwegian Algebra Challenge a year ago, in which 30,000 students solved nearly 8 million algebra equations in a week. And what's really interesting is the test of mastery was the same for first graders and 12th graders. And although it took first graders longer to get there, the same 90-some% passed the mastery test, which was solving 4 fairly sophisticated linear equations. The same proportion of first graders as 12th graders, and the game was interesting enough that it kept them in it. And at the same time, the 12th graders got to the end fairly quick and moved on to recess or whatever, okay? So again, the last thing anyone would assert is you're replacing teachers. The goal here is to allow teachers to spend their time in a place where it does the most good. That's the idea. Smart interaction, things like Connect and HoloLens. Smart cities, we're involved in an urban project I'll talk about in a minute. Smart discovery. Now we're on to sort of the big data for science, and this is how I've been spending my time in the past few years. So what's happened is every field of discovery is moving from data poor to data rich because there are sensors everywhere. Jim Gray, my now deceased colleague at Microsoft, referred to this as the 4th paradigm, and his argument was we spent centuries in empirical science, then we transitioned and added to that a theoretical component. We added to that in the 1950s a computational component, really aided and abetted by the National Science Foundation investing in supercomputer centers. And now we're adding a data-intensive component. And I always have to say that these paradigms augment rather than replace the previous ones. My computational science friends always accuse me of attempting to diminish their importance. And all I'm trying to say is that something else is becoming as important, and you no longer have the whole show. So the challenge for discovery, right, is translating now vast amounts of data into actionable information. And in many cases now, the Sloan Digital Sky Survey is a great example. Astronomy was transformed by Jim building the data system for Sloan, along with Alex Zelle, an astrophysicist at Johns Hopkins. Suddenly, all of the data was available to everybody, from school child to PhD astronomer, at the same time. And your competitive advantage was how fast you could discover interesting things in that data. It was no longer getting the data. Okay? For decades, it's been getting the data, and now in many fields, we're drowning in the data, and the question is, can you extract knowledge from it? So our pitch when we first started the eScience Institute at the University of Washington, which was in about 2007, was, look, computational science, numerical computational science is going to continue to be very important, but it's well established. And really what we need to do now is to subsidize, invest in the intellectual infrastructure for data-intensive discovery, which is going to be totally pervasive. A sociologist who wants to study the creation and evolution and dissolution of cliques used to pay a bunch of students $6 an hour to participate in a focus group at lunch, and now she's trying to get her mitts on 1 billion users worth of Facebook data. That's the social network, the clique, okay? So this work has been supported by the University of Washington, by the National Science Foundation for a graduate program, by the Moore and Sloan Foundations, a collaboration with Berkeley and NYU that I'll talk about in a minute, and by a local foundation at the University of Washington, the Washington Research Foundation. And by and large, I'll say this again in a minute, they're investing in social engineering. So here's what happened with the Moore and Sloan Foundations. They do not care at all about computer science, statistics, applied math. They care only about the social sciences, the physical sciences, and the non-human life sciences. But they were smart enough to realize that there were new modes of discovery and new discoveries that were possible, and there were a set of institutional impediments to driving this out on campus. So what they did, beginning from a derby of 15 schools, was to identify 3 of us who were not only had methodological data scientists engaged with scientists in those fields, but who had a set of deans and provosts and presidents who were willing to run some experiments with things like reward systems. And it is an experiment. It's a distributed experiment. We've agreed to share what doesn't work as well as what does work. And the hope is that the 3 universities working together can actually figure out how to accelerate the dissemination of this. This is our picture from the beginning. And the way to think about this is everybody has a set of data science methodologists. Those are the red boxes on the right. Everybody has a set of scientists in the areas the foundations are interested in. Those are the blue boxes on the left. And the impediments we identified as we started this project now 2 years ago are the ones in green in the middle. It's things like lack of career paths for people who build tools and who accelerate other people's research, as opposed to being their own first author hero, right? It is how do you educate students to be strong both in the methodology and in some field where they're utilizing the methodology? How do you build software tools that accelerate science when in fact there's lots of money to build software for accelerating business? Business has been much faster on the uptake of this stuff than discovery has. The foundations are extremely interested in reproducibility and open science. You get the picture, okay? And the goal here is to create this virtuous cycle in which new data science methodologies accelerate new discoveries, which motivate the need for new data science methodologies, and you go around the loop, all right, faster and faster. So that's what we're trying to do. Our original team at the University of Washington has a large number of people from applied math and statistics and computer science, but also people from the life sciences, the social sciences, the environmental sciences, and the physical sciences. They represent 13 departments and 5 schools and colleges. So this has been the most fun I've had in 38 years at the University of Washington. And because, in some sense, only good people were willing to take a risk on this, we've been able to cherry pick, you know, the best neuroscientist, the best oceanographer, the best astronomer. So it's been just a phenomenal experience. So here are 4 quick science examples. Andy Connolly was Alex Zelle's chief postdoc when Alex was doing the data system for Sloan. And he's now a kingpin of the Large Synoptic Survey Telescope. This is the next big survey telescope project. And the LSST will capture 1,000 times as much data per day as the Sloan Digital Sky Survey did. And the Sloan Sky Survey was totally revolutionary. And what's important is that this really changes the astronomy in 2 ways. First of all, it is vastly higher resolution. And the photo on the right is a simulation of what LSST will get. The one on the left is a photo from Sloan. but additionally, because you can scan the same area of the sky multiple times in a night or a week or a month, you can do time series analysis, and that's never been possible in astronomy before. So an example of work my colleague Magda Balazinska, who's a top data management person, has been doing is designing data management systems that allow that sort of temporal analysis to take place, 4-dimensional instead of 1 or 2 or 3-dimensional data. So this is a slide from Andy, and I'm really pleased that our astronomers come up with slides like this. He says, look, we got these science questions. How do you find things like supernovas? How do you find moving sources like asteroids? Mapping the Milky Way, measuring the shapes of galaxies. These all have computational analogies, right? And that's what's revolutionary. There is a computational statement of each of these astrophysical science problems, okay? And so facilitating the computational techniques that accelerate that astrophysics is a key component of what we're trying to do. This is a video from my neuroscience friend Tom Daniel and Bing Brunton and Adrian Fairhall. Tom's research involves something called a hawk moth. It's a moth you don't want loose in your closet because it has a 4-inch wingspan and a voracious appetite. They have somebody in the basement of the biology building who grows these things. They have a moth factory. And Tom has a virtual reality environment. The moth is flying in the VR environment. You're flying through a forest. And I don't know if you can see, but there's a little pole that you can see occasionally going to the back of the moth. One of the great things about doing research on moths is that, PETA doesn't get upset there, Okay, so the idea here is the moth is glued to a joystick, and as the moth flies back and forth, it deflects the joystick, which manipulates the virtual reality environment, okay? And the moth is instrumented. There are a number of wires going into what passes for a brain, and Tom is collecting vast amounts of data from this moth, and he doesn't really care about moths. What he cares about is how do you extract features from your environment, process those, translate them into muscle activity, which then changes your perception of the environment and go around the loop. All right, so that's the experiment. And it's in every way a big data problem, but it's absolutely at the forefront of neuroscience. Ginger Armbrust is the director of our oceanography program. She does environmental metagenomics, and I won't bother to describe that because we'll really run out of time. But think of her as doing a form of comparative gene sequencing. And we built for her a tool called SQL Share. She was doing this analysis, which to me sounded like a database operation, by staring at spreadsheets. And there were a couple of reasons. One is 5 or 6 years ago, the data volumes could be stared at. It was only taking, say, a person day a week to do this, and that was a justifiable amount of time. Secondly, she didn't want to run a database system. She didn't know what a schema was. She didn't speak SQL and things like that. So SQL Share is a system that takes the data out of her sequencers, crams it into a cloud database without a schema associated with it, and then by an interview process we learned from Jim Gray, her 15 most common science questions show up in a window on the left, and when you click them, the SQL, the database language to answer the question, shows up. And pretty soon people who couldn't write SQL are editing it into an adjacent query, and before long they're writing it. Okay, so this system has just transformed the work of her lab. Another problem for her is integrating across different data sets. So typically, the oceanographers go to sea, they collect the data, they bring it home. You will have physical and chemical and and biological oceanographers on the same vessel. They'll each collect their own data. They each take it home, okay? After one of these cruises, Ginger decided 6 months later to get the physical and chemical and biological oceanographers together and spend 3 days planning for what science they could do if they were to collaborate. And instead, the screen has just gone out. Instead, what we did was, and we always mean someone who works with me, not me, okay? We put the data into SQL Share and sent a postdoc and a graduate student who were experts at data management, and they spent 3 days actually doing science. It was unbelievable, all right? And, doing science that the biologist could not have done alone. Okay? Another problem she has is connecting over distributed labs, and again, we've just automated that for her. So now the people in the lab in Seattle or elsewhere get the data at the same time it flows off the instrument onto the ship. Here's a final example, and then I'll move on a bit. We ran a program this summer that we cribbed from the University of Chicago and Georgia Tech called Data Science for Social Good. Right? And this was a research project. There were 4 teams. Each of them involved 6 undergraduate or graduate students and one or two high school students. Okay? And some of our data scientists. And those are the problems. Let me just show you one of them. These were all proposed by external parties. So the Gates Foundation proposed one related to predicting whether homeless individuals were likely to find permanent housing as a function of what processes they go through as they become homeless. Okay, so this, again, we won't spend any time on this, but it shows various pathways you can follow, like from one emergency shelter to another, and what the likelihood is that at the end of the road you wind up with a successful exit, meaning you found some kind of permanent housing. All right? And they looked at all kinds of interesting ways like interactive Sankey diagrams to visualize this data. The Gates Foundation had paid a couple $1 million to consultants to work on this problem for a year, and they produced nothing, right? And these students with a bit of supervision in 3 months produced something that really transforms the program for the Gates Foundation. So they're now funding a follow-on study. This data science for social good, I think, is a huge home run because everybody wants to solve societal problems, and there's a huge amount of urban data that's available and underexploited. Okay, so let me now look a little more closely at these data science environments and emphasize that they are social engineering. And again, I'll go through this quickly. In career paths, let me just highlight one thing in each of these. We have recruited a set of data scientists who are professional full-time people whose job is to accelerate other people's research. And that's been just a complete home run for us. These people have been extraordinarily valuable. They are on publications, but that's not their job. They are not faculty appointees. An analogy is the University of Washington has a strong oceanography program, partly because we have a terrific applied physics lab, which has about 100 research engineers, okay, many of them PhD educated, whose job is not foremost to educate PhD students or undergraduates or to publish papers. It's to build the instruments, the floats and the gliders and the instrumentation that the oceanographers use. And those people have enough surety of employment that they stick around, and they're just incredibly important to our success. So how can we do this for data science? Another thing we did that's been very important is the provost gave us 6 half-faculty positions, and we use those for social engineering. What happens is that there are various versions of this, but roughly, if an academic program wants to hire somebody who is very strong both in advancing data science methodology and in the field of that department, then we can elect to recommend to the provost that she provide half the funding for that person in perpetuity. And in return, we get half of that person's teaching cycles and half of that person's service cycles, and we sit on their promotion and tenure committee. All right, so we've made 6 hires in this program so far, and they've been utterly phenomenal people. Really, really phenomenal. And it's a way, it is social engineering. It's a way to get departments to move earlier than they might, or in a different direction that they might, in a way that's good for the campus as a whole. We have, as I mentioned, an IGRT PhD program in big data. And an example of the social engineering here is that if you want to be part of this IGRT program as an academic department, you have to agree that our data science courses replace a set of the courses that you otherwise require for your PhD program. And for all students, not just the IGRT students. So you have to be all in, right? We have a set of postdocs. By the way, all the IGRT PhD students are dual mentored. They're in one department, but they have a faculty member both in a methodology field and in their applications field, if they're in astronomy or biology or something. We have a set of dual mentored postdocs. One of the social engineering problems we solved there is the 12 departments involved in the first cohort of postdocs had postdoc salaries that differed by a factor of 2. And you can't have people of the same seniority in the same lab doing the same stuff getting salaries that differ by a factor of 2. So if people wanted to play with us, they had to agree on a standard salary. We run tons of workshops and seminar series as part of education. In software tools, the important thing we have is an incubator program. The Data Science for Social Good was an instance in this, but twice a year, we run a little 2-page lightweight proposal derby. And people can propose to us by saying, look, I got the following science problem. It has a data science element that I don't know how to tackle. I think it's interesting enough that if you solved it for me, that solution would be useful to others, and I'm going to come and spend half time with you for 3 months to provide the labor. So we're in the business of providing free expert advice, but not free labor. All right? People from all across the campus have taken advantage of this. We have office hours and things like that. Reproducibility, let me not say much about this, except that I believe that reproducible research is in many ways a tools problem. All right? If you don't make it as easy to do your research in a reproducible way as it is to do it the way we do it today, then people aren't going to do it because I'm not even willing to take the time to do my research in a way that I understand it a year from now. that I can reconstruct it, much less that you can reconstruct it and build on it. Okay, so for example, one of our colleagues at Berkeley, Fernando Perez, is the creator of IPython Notebook, which is just a phenomenal step forward in tools for reproducible research. We converted the physics astronomy library on the top floor of the physics building. That's its previous life as a library. Heather actually mentioned she used to study there. That's not her. There must have been a second person there at one point. Into a data science studio, which is just fantastic space. You know, there was a time in the past when we would carry boxes of cards to a computer center. While we're waiting for our listing to come back, we'd have nothing to do except talk to the other people there. And we discovered that although we were in different fields, we had problems and solutions that were in common. And when computing retreated to the desktop and the cloud, that went away, okay? And data science is really, I think, the water cooler for the next several decades. And we've had a number of examples of people in one field having a solution useful to a person in another field, and the only way they discovered it was they're hanging out in this space. It's been incredibly valuable. By the way, at both Berkeley and the University of Washington, it's the libraries who put up the space. And the reason is they're trying to figure out what the heck a library is in the 21st century, and data curation and stewardship is part of it. So the libraries have been utterly phenomenal partners. We have an ethnography team at all three campuses led by somebody at the University of Washington. This was a word I didn't know, right? But before starting this project, if you are going to try and affect the way in which discovery is done, you'd better be able to measure that. And this has been really important. Okay? And finally, just general role of a catalyst. For example, I think it's important that we have really kept the eScience Institute as something that doesn't belong to any one department. And there is a land rush going on now, and everybody's getting very grabby. And that includes my own department, Computer Science and Engineering. When we first got the IGRT, which was a proposal written by people from 6 departments, one of my computer science colleagues immediately decided that this were to be a computer science-dominated graduate program. Now, my aid in beating that back was his wife, who's a faculty member in statistics, okay? So he was getting it both at work and at home. But it's important, right, that we can make sure that this truly interdisciplinary field, even on the methodology side, right? It's not just computer science, it's stats, it's applied math, it's human-centered design and engineering, it's our information school. All of them are in the business of creating the way to do this. It's not owned by anybody, and we can make that happen. Same at NYU and Berkeley. Okay, so this has just been a phenomenal project. Let me now do these little 1-minute things, and then we'll have time for questions. I'm actually going to end approximately on time. This induces what I think is a modern view of computer science that we've tried to espouse, and I think it's catching on. This is the stuff we've been doing for decades. We've had 50 years of building faster, better computers, all right? This is operating systems, programming languages, computer architecture, compilers, artificial intelligence, you know, and it's great stuff, and it's still important, right? There are still advances to be made. Those advances are critical, but this is what people care about. It's societal challenges, it's education, it's health care, right? You know, it's babies. Okay, and what's going on these days is that the core of computer science is connected, right, to those societal challenges by a set of emerging areas, things like natural language processing, robotics, sensors, data science, all right? We do all of this stuff, and at the University of Washington, the majority of our investments in faculty in recent years have been in those gray areas, those connecting areas, and we have somebody whose research is focused on essentially every one of those societal challenges in our department, okay? So the natural question is this stuff computer science, right? And 20 years ago, 10 years ago, we would have completely disowned it, okay? And my feeling, though, is that while the last 50 years of computer science was judged, success was judged on how much faster things got, right? I think the next 50 years is going to be judged on what kind of impact we have on solving problems people care about, which is not your programming language or your compiler, okay? And my motivation for this is an article from 1998 in Spectrum, the IEEE magazine, by Bob Luckey when he was running Bell Communications Research. And the last electrical engineer was not the title, but it was the money phrase. And this thing on the lower right is the cartoon that accompanied the article. And what you see is a single person standing underneath this inverted pyramid. On top of the inverted pyramid are all the people doing applications, right? And what he said was, if we disown all that stuff as being somebody else's business, then eventually there's only going to be one of us, right? And that person would be very well compensated, but it's not enough people to sustain a field, right? And Lucky meant this as a ding on electrical engineering, and what he was envious of was computer science. But I took this as a cautionary tale for computer science, right? And we were, even 10 years ago, disowning anybody who wasn't doing operating systems and compilers, with rare exceptions, okay? So I think the important message here is to take a broad view of the field and embrace this stuff as part of what we do, obviously in partnership with others, right? It's not like we're going to do medical technology by ourselves, for gosh sakes, but these are opportunities, and we have to embrace the people who do it. So Alfred Spector, formerly of Google, referred to computer science as the ever-expanding sphere. There's a sort of negative manifest destiny view of that, but I tend to interpret it instead as just, you know, it's this field that gets bigger and bigger and has more and more impact, and we should embrace that as part of what we do. Let me talk about educational trends. This is incoming freshman interest over the past 8 years at the University of Washington, all right? This is computer science and other fields of engineering. We're housed in the College of Engineering. By the way, our capacity per year is about 300 new students, and this 850 dramatically understates student demand because while some of those will deselect, a large proportion of our students, particularly women, discover our major through the introductory course. 58% of the women who become our majors did not have that intention when they took the intro course, okay? Here is computer science compared to all the other majors at the University of Washington. So in terms of freshman interest, we've passed biology, and we're going to eat business alive next year, all right? So demand is growing like crazy, and this is true across the country. And of course, universities are terribly slow to respond for a variety of reasons, and we'll have to see what the impact of that is. But I think it's important to realize where the student interest is these days. And part of it is technology is hot, but part of it, I think, is that people are realizing that computer science is a change-the-world field. Advanced placement participation in computer science is still pathetic, but in the past 5 years, it has grown from 20,000 to 50,000. So it's now, from a very small base, the fastest growing AP exam, which bodes well. I think a lot of this is because things like code.org is really increasing interest among K-12 students. Code.org, now more than 100 million students have done the hour of code around the world. More than 7 billion lines of code written. This is a Seattle operation. Hadi Partovi is a friend of mine who's an ex-Microsoft and startup person who a couple of years ago decided he was going to do something about interesting more kids in computer science. And it's been completely revolutionary. So he's now in the business of teacher preparation to drive this out into the schools. However, 9 out of 10 high schools don't offer computer science. In 24 of the 50 states, computer science does not count towards the math or science graduation requirement. That's much better than it was. 2 years ago, only 14 states counted computer science towards the math or science graduation requirement. In other states, it's a shop course, all right? Like typing and metal shop and wood shop, all of which I took, and typing at least was something that was good for me. You know, and so we're up from 13 or 14 to 26. I can't resist pointing out that the state of Colorado is not one of them, okay? So there's a job for you folks, which is to get your state to count AP Computer Science as fulfilling a math or science requirement in high school, okay? I have to say that computer science and my friends at Microsoft are partly responsible for this, and that is that everything from keyboarding to PowerPoint and Excel to the intellectual content that is AP Computer Science were all called computer science. And part of what happened was the colleges just said, look, if you folks can't sort it out, we don't want any part of it. In fact, until 2 years ago, for a decade, the NCAA would not count AP Computer Science as an academic course for a prospective college football player. Okay, and it's because of this. It's because we screwed it up by originally trying to sell keyboarding and then trying to sell PowerPoint training as something that you should get academic credit for. Okay, but this computational thinking is something everybody needs in the 21st century, and our kids have to have it. They have to have it not because they're going to go work for Microsoft or Google or Amazon, but because the way in which we think, modeling and abstraction and algorithmic thinking and algorithmic expression and stepwise fault isolation, which we call debugging, is essential to everybody. Workforce trends, I'm almost done. This is BLS data on newly created jobs in the decade in all STEM fields. Let me state the caveat here, which is that being a health professional is not considered a STEM occupation. Being a biologist or a biochemist is a STEM occupation. So there's that bogosity here. But what you see is that BLS projects that 71% of all newly created jobs in all STEM fields in this decade will be in computer science, okay? 15% in all the rest of engineering added together, 3% in the physical sciences, 3% in the life sciences. You get the picture. If you choose to look at available jobs, whether newly created or due to retirements, computer science drops to a mere 57%. Okay? Computer science and other fields of engineering are about 85% by either major. So that's where the jobs are as well. I said I would talk quickly about entrepreneurial opportunities. This will be very superficial, and not all of these are startups, of course, but many of them are. And this is sort of a Seattle view. There are obviously huge opportunities in infrastructure and Amazon Web Services, Azure, the Google Cloud Platform, Cumulo and Isilon are Seattle originally startups in sort of the network-attached storage business. There are tons of room for innovation and tools. Tableau is a Stanford spin-out that chose to locate in Seattle a dozen years ago and now has 2,500 employees. They are absolutely the leader in visual analytics. This is the picture is worth 1,000 words. Trifacta is a company started by our faculty member Jeff Hare that does data cleaning. Dato is a scalable graph machine learning company started by our faculty member Carlos Destrom. There are just, again, tons of opportunities. There are lots of verticals and services. Again, this is a Seattle view, but Zillow is real estate data. Socrata is a Seattle company that is the world repository for essentially jailbreaking urban data and making it available to those citizens and decision makers. Inrix is a Seattle company founded by some ex-Microsoft people that has all of the traffic data from the major cities of the world, instantaneous traffic flow data. So they provide routing recommendations instantaneously, but also recommendations on, for example, they're the reason that UPS makes 3 right turns instead of a left turn, all right? This sort of stuff. The chief scientist of INRIC spoke in my course last year, and the kids wanted to know what a chief scientist did, and he gave the following example. On highways that have HOV lanes, you see this bimodal distribution of speeds. By the way, they get this data partly from sensors in the road, partly from fleet vehicles, and partly from smartphone apps. If you use the smartphone app, you're sending them GPS location information. The GPS says where you are on the road, but not what lane you're in, okay? But the bimodal distribution, you can confirm, is the obvious thing. It's the HOV lane and the other lane. One moves at 60 and one's moving at 25, okay? So what do you do with this data? They're selling it for a bundle to electric vehicle sales companies and manufacturing companies in California because a single occupancy EV gets you into the HOV lane, all right? So the first tranche of buyers all bought Priuses because they were distinctive cars and you could show that you were environmentally conscious. The second wave of buyers all bought Teslas because they were excellent, expensive cars, and you could show that you could afford to spend $90,000 on a car, okay? And the idea is that the next wave of buyers are people for whom time is money. And I can say to you, Bob, you live here, you work there, you tell me you leave home at 7 in the morning to go to work, and you leave work at 6:30 to go home. Here's how many hours a day you will save by buying our electric vehicle and getting yourself into the HOV lane, all right? Sensor systems, these again are Seattle startups, all kinds of intensive users. This open data movement in civic data is gaining a huge amount of traction. One Bus Away is an app that a student of ours did as his PhD thesis that uses transit data from a number of cities to tell you exactly where your bus is and when it will get to your stop. You can, set alerts on it and stuff like that, but there are lots of other examples. Okay, finally, and I'm almost done, support for 21st century cyber infrastructure. Many fields of discovery are becoming information fields, but we continue to have policies that argue against sensible behavior in computing, okay? And here's an example. The use of commercial cloud resources is advantageous in many, many ways, but it's discouraged, first of all, by the fact that you pay indirect cost on outsourced cloud services, but not on equipment that you buy, right? So for me to get $100,000 of AWS credits from NSF cost me $157,000. For me to get $100,000 worth of gear cost me $100,000, but it's even worse because what really happens is my computer science program director at NSF says, oh no, go to the major research infrastructure program, which is not charged against any directorate. So it actually costs the computer science guy nothing to buy me $100,000 worth of gear. Okay? It's utterly crazy, right? We love buying stuff. We hate using commercial solutions. What Jim Gray did for Sloan was to convince them that large-scale astronomical science data could be housed in a commercial relational database system. Nobody had done that before because the world is full of people and organizations whose paycheck is dependent on convincing you that no commercial solution could possibly meet your needs because you're special. Okay? So, you know, we are constantly rolling our own and running our own and buying our own. The commercial cloud has infinite capacity. You pay for what you use. It scales down as easily as it scales up. There's no capital cost. Somebody else provides operations support. Somebody else handles backup. Collaboration is incredibly easy. It keeps getting bigger and faster and less expensive in contrast to the system you buy, which is the same in 3 years as it was today. Here are some things we could do. One is, as universities eliminate subsidies. You know, at a university, Santa Claus pays for the power and Mrs. Santa Claus pays for the cooling and the elves do the backup. All that stuff appears to be free until the system crashes and you discover that the elves didn't do the backup, okay? And then you lost 6 months of data, right? But this creates a false sense of what costs are and therefore a false inflation of the costs of services where you actually do that stuff. The University of Washington 5 months ago did something utterly revolutionary, which is they have unilaterally forsaken indirect cost on outsourced cloud services. This is huge, okay? So outsourced cloud service, and again, as long as it does this uniformly, a university can choose not to collect indirect cost on something, to waive it, okay? So we hope this catches on. We've been trying to get the National Science Board to move in this direction, but that's like kicking a dead whale along the beach, right? But I think this is really important. Attribute MRIs to directorates. And I think that the use of cloud services should be the default. If you want to buy gear, then you ought to have to say why. Okay? Let me not belabor this. I think this is just a phenomenal time for all of us. The nature of discovery is changing. The nature of computer science is changing. And it's going to change the world. So thank you for your attention. I'm happy to take questions. I think for the benefit of people at the remote sites, there's some microphones, and can we run those down here, or are they on cords? Perfect. Hang on one sec. Thanks, Megan.
Thank you, Dr. Lazowska, for a fantastic presentation of a fantastic world of new science and technology that promises and already delivers fantastic benefits for humanity. So I don't want to spoil the party, but what about the negatives of this? Can we ignore them? For example, the Genome Project and related big data carries the risk of health insurance companies will deny me insurance based on the fact that my genome shows that I'm prone to certain genetic diseases. There is government security agencies are recording every phone call, data on every phone call we all make.
Yep.
And I could go on and on. Companies monitor all my shopping habits and practically every habit that I have. So my question then is, what do you, your colleagues, and all the people who create this fantastic, brave new world, what can you and what do you do to prevent the negatives?
So I'm going to give you an unsatisfying answer, but I will try. You know, it seems to me that every technology has both negative impacts and applications and positive impacts and applications. And you have to accept both of those and do what you can to mitigate the negatives, right? And I'd recommend to you, by the way, John Markoff from the New York Times has just published a new book that's out a week or so ago about robotics and artificial intelligence. And he's talking about exactly this issue, less in the privacy realm than in the jobs realm, okay? That is, there are two dichotomies he talks about. One is artificial intelligence versus the augmentation of intelligence, all right? Those are two dramatically different approaches to AI going back to the start of the field. But the other is that even the people who are just creating technology to make us more efficient, more effective, are eliminating jobs. And what's our responsibility to do something about that, okay? Now, my feeling about privacy is that the cat's out of the bag. We can forget anything that we do being private, and what we need is, among other things, laws related to the release and use of information, right? And we're way behind the 8 ball on that. Microsoft funds a thing called the Technology Policy Institute at the University of Washington, and the principals are somebody from the law school, Ryan Kalo, a security and privacy person from computer science and engineering, Yoshi Kono, and a woman from the Inspiration School, Batya Friedman, who studies what she calls value-sensitive design, right? And the important thing about these problems is they have no solution that is purely technological or economic or social or legal. You need to be moving forward on all of those fronts. And I think what Microsoft is trying to do, I give them a big benefit of the doubt here. They are not dictating outcomes. What they really want is for people to be thinking about these issues not too late, right? And I think that's the important thing. I think the human genome community was a little late to the party. The synthetic biology community was a little late to the party in considering these things, and we're undoubtedly late to the party too, but you're absolutely correct, of course.
One of the drawbacks I've heard with big data is you can, obviously if you have, the more data you have, the easier it is to find correlations and find any sort of connection. When you process all this data, what do you do to make sure that you're not just finding, random correlations and you're actually finding, true results?
So there are two different issues. One is sort of statistical. It's the danger of overfitting, which people do all the time. And there was a recent article claiming that, for example, something like 50% of a set of psychology papers could not be reproduced, and overfitting was one of the villains there. The other danger is drawing unintended and unwanted correct correlations from vast amounts of data. And that's back to your privacy problem, all right? So, and there are some technological solutions. There's, for example, something called differential privacy, which Cynthia Dwork has won the Turing Award for a couple of years ago. So there are some technical approaches, but I think there have been many examples of technology companies releasing data for research purposes that they thought was thoroughly de-identified, and nonetheless individuals being able to be identified from that data. Okay? So I think there are problems on both sides. There are problems of drawing erroneous conclusions, and I have to say that in any data management, data analysis problem we've been involved in, the biggest challenge by far has been dirty data, right? You never get clean data, so you're constantly in danger of drawing false conclusions from dirty data or from lack of knowledge data. I mean, here's an example. The Institute for Health Metrics and Evaluation at the University of Washington is one of two organizations along with the UN that is sort of the yardstick by which progress in global health is measured. And Chris Murray, who runs it a couple of years ago, turned his lens on U.S. health. And one of the things he observed, and those of you who are physicians are thoroughly familiar with this, is that because of coding differences, there are situations where a disease appears to be rampant in some state and non-existent in an adjacent state, okay? And so, is pneumonia due to AIDS coded as an AIDS death, as an example, okay? Yes, in some states, no in others. And so you need sort of inside baseball knowledge in order to be able to draw accurate conclusions. So again, there are two issues here, and they're equally difficult. One is drawing false conclusions from vast amounts of data. Another is drawing undesired but correct conclusions from vast amounts of data. And we're doing both of those things, and we have to work harder. I don't have a good answer. Another question?
I guess given all the different software programs, different programming languages and stuff, what sort of trends do you see, I guess, in the actual software and programming languages, given like R being out there right now and, compared to a Python or something like that? I guess do you see the open source winning eventually, or do you see a convergence, I guess?
People use everything, all right? I think the important issue is that we in computer science are very good at building tools that only we can use. And to me, the challenge is producing tools that people who aren't us can use, right? And it is clear that R, which we didn't produce, is a programming language that people who aren't us can use, right? Database systems can't be used by people who aren't us. And an important challenge is to make data management. This is something that SQL Share does. It makes relatively modern data management usable by oceanographers who have no computer science training, right? There are a number of efforts at companies these days, including Microsoft and Amazon and Google, to make machine learning usable by others. And the question is whether you can blindly apply machine learning without drawing completely bogus conclusions to the previous question or not. We will see, but there's some very good people working on that. But to me, making data management and machine learning usable by people who aren't us is the critical challenge right now, even more than making programming languages usable by people who aren't us, because most people shouldn't be writing in programming languages anyway. It seems to me they should be using tools. Tableau has been really successful. And how many of you use Tableau? It's phenomenal. And there's a web-based version you can use for free, and it's used by everybody from businesses to scientists to people running fantasy baseball and football leagues. And their tag phrase is visual analytics for the non-specialist. And to me, that's the right tag phrase. In the long term, you don't want there to be a data scientist on your team. You want to be a scientist who is facile and able, because the tools we provide, to explore your own data. If you have a data scientist standing between you and your data, it's like the 1970s when you had a database administrator standing between you and your data, and you had to beg that person for 3 months to produce a new form for you, a new report. And even when you eventually got it, it wasn't what you wanted. Okay, so the challenge for us, I think, there's a question about data science, about whether it's going to go the way of computer science or computational science. And here's what I mean by that. I think computer science is a valid field. It makes sense for there to be academic programs in it. People get jobs in it. There's some substance to it. I hope that perception lasts at least until my retirement, okay? At the same time, you don't see many programs in computational science, and you don't see people getting PhDs in computational science getting hired. You see people hiring computational chemists and computational biologists, all right? And my personal view is that data science is going to go that way. It's a valid place to have master's programs. It's a valid place to have tracks in PhD programs. But eventually, my feeling is that most scientists are going to be data scientists, because that's how we're making, part of how we're making discoveries, okay? And so you want to sort of banish the data scientist and have people practicing data-intensive discovery in all sorts of fields, and have us giving them the tools and education that make that possible. Sir.
Thank you for a very exciting look at the future. Let me ask you a slightly cynical question, however.
Didn't we already have that?
This is a second cynical question.
Thank you.
I'm very excited that I would love to be planning and looking at the next 40 years of my career that you see, but I'm unfortunately looking at the last 40 years. And there have been a couple of little problems in here, and I'm wondering if you guys have given any thought to this, about the practical question of how you evaluate for tenure and for retention, for example, in your department. Suppose I join your program,
right,
as a 30-year-old coming into the department, and I participate in 10 different programs. I publish 10 papers with 40 people. How do you calculate?
Sure.
And how do you evaluate the performance? Because it seems to me in large interdisciplinary studies, which I participated in, and I really think they're very valuable, there tends to be a leveling and a dilution of being able to find the contribution that you can use for tenure kinds of questions and retention.
So, of course, I agree with this, and this is a concern of ours for sure. So let me talk about what we're trying to do at various professional levels, okay? For the PhD students and the postdocs, they are in some field, all right? And what we're trying to do is to make sure that they are mentored in two fields and develop capabilities in both of those fields, all right? But the expectation is they are a biologist or an astronomer or a statistician, all right? They are not a sort of data scientist, all right? So the goal is to put them in an interdisciplinary environment that ultimately is going to make them far better at what they're doing, all right? At the level of the undergraduates, what we have is a set of tracks that fit into a set of programs, okay? So they get a note on their transcript that says they did the data science option. Again, it just makes them hopefully a better biologist at the bachelor's level, right? At the professional staff level, I think there are models in things like the NSF supercomputer centers and various state university supercomputer centers and our applied physics lab of people who are often PhD educated, whose job is accelerating other people's research, and who are part of a large enough organization that they have stability of employment, right? Without having to individually sing for their supper, right? And so, you know, the engineers in our applied physics lab don't worry about whether they're going to get a paycheck next month because of one particular grant. Okay, it's an operation. There's a lot of rain that's made by a lot of people. Okay, so I think these professional staff members are going to have fine staff careers, and the important thing is that we create an environment for them that offers professional stability and professional rewards, right? And you know, for example, none of them were social scientists, but 5 of the 6 data scientists really dug into this data science for social good this summer and made it fly and had the time of their lives. Right? It's just, I think, really exciting for them. They come from a range of backgrounds. For faculty, I think we'll see how this goes. Let me say that the faculty who were already at the University of Washington, people like Tom Daniel and Ginger Armbrust and Andy Conley, are superb people who are honestly what we call pie-shaped. They are capable both of advancing the methodology and working in their field, but among people in their age range, which is, let's say, 40 to 55 or so, they're pretty exceptional, right? For the younger people we're bringing in, there is a commitment by their home departments to, now again, these people are, they are not doing other people's work, they're doing their work, all right? They are an astronomer, a sociologist, a neuroscientist, a mechanical engineer, right? But they also make methodological contributions and publish in the methodology literature. So we will see. We sit on their annual review committees. We sit on their promotion and tenure committees. So far, it's been smooth sailing. There has not been anyone coming up for tenure yet. There have been a number of people who have sailed through their midterm 3-year review. Again, they're pretty extraordinary people, and they were hired by academic programs that were willing to buy into this. We'll have to see. The provost is providing oversight on this. I hope we're not risking anybody's career. Let me state one other source of optimism. This is back to the Sloan Digital Sky Survey, and it's through the lens, through the eyes of Andy Connolly, my now mid-career astronomy collaborator. Andy was a postdoc during Sloan, and what happened was a small number of faculty members were willing to take a risk on survey astronomy, and they had a set of postdocs, and those postdocs took a risk. But by several years later, and astronomers do multiple postdocs, the winds were blowing in the direction of survey astronomy, and everybody else realized, every other astronomy department realized that it better be in that business, okay? And so the first couple of cohorts of Sloan postdocs got many of the best jobs in astronomy 3 and 4 and 5 years down the road, okay? Because they were the people who could do this. And my belief is that the people who don't understand the potential of data-intensive discovery in their field today are going to understand this in 2 or 3 or 4 years. I mean, you know, we faced, honestly, bitter opposition from our former provost and our vice provost for research when we started this data science effort back in 2008. And it wasn't at all obvious that we were right. In hindsight, it's obvious that we were right, right? And that's 7 years of hindsight, but not a lot. I firmly believe that the most productive sociologists and the most productive neuroscientists a couple of years from now are going to be the people who can do the data discovery. And hopefully that's what we're positioning the postdocs for. They're taking a risk for sure. The one thing also I would say is the fact that UW and Berkeley and NYU are doing this together adds a certain amount of sort of confidence. At the very least, we'll hire each other's postdocs, all right? But the hope is this will be contagious, and that's what part of what the Moore and Sloan Foundations wanted to do is conduct an experiment among places that might be influential if it worked. Thank you. Thank you so much.
Thank you very much for the magnificent lecture, despite my concern about privacy.
You're absolutely right.
I'm just a dumb chemist. You have a great delivery. Thank you so much.
This was tons of fun. I've enjoyed it thoroughly. Thanks again.
I think you'd have kept it going for quite a while.
Sorry.
That was great.
Good to see you. Thank you so much.
The School of Public Health.
Good to meet you.
Wasn't able to be at your meeting earlier.
It was
today.
wonderful.
Anschutz campus.
What a great